Good morning. So I've got the exciting first slot then. I can hopefully keep you awake between now and about 10. I think I'm going to go to. So while I'm doing this presentation, if you want to ask any questions while I'm going along, that's fine. Or if you want to hold them to the end, it's pretty informal, so I don't mind, however you prefer. Look, I need that. No. So I've done it already. I was doing an introduction about what I'm going to talk about, and the idea of these presentations is to give you some idea of what we think might be going to happen in a particular sector or application over the coming few years. And I want to talk about energy challenges, and then the hydrogen economy, which I guess everyone will have heard at least the title of, and what I think of that, and then possible alternatives including the ammonia economy, some chemical and thermal storage, and some other techniques, and then an outlook. I forgot to say that I am a chemist, so I work in the chemistry and biotechnology team here, but hopefully I won't go into too much chemical detail for those people who aren't chemists, so you won't be utterly baffled by what I'm going on about. Well, I think we can all agree that novel energy generation is pretty well supported. So if you've not got any idea what I'm talking about at this point, you can see here, these things are all over the news at the moment. We've got wave power, wind power, tidal power, solar thermal, photovoltaics and hydroelectric. So these things have been about for actually quite a long time now, most of them at least a decade. But the generation part is easy. I put easy as perhaps should be in inverted commas. The storage part is actually the difficult bit. And at small scale, the best technology still really, in terms of portable energy storage, is the old lead acid battery, invented in about 1890. So you can see it's certainly doing well for something that's pretty old. And there hasn't really been a huge amount of research in that for 70 years, thereabouts. And at large scale, we've got this. I'm not going to attempt to pronounce in Welsh the name. This is a dam, a hydroelectric power station, effectively. When energy is required, it kicks in, drains the top lock through the hydroelectric power station to the bottom lock. And when there's an energy, there's too much energy, if you like, in the grid, it's used to pump the water back up again. Interestingly, the issue with that is that 40% of the energy that's gained from letting the water down is used to pump it back up again, 40% more. So you see, it's not particularly efficient. But that, at large scale, that's the best that currently exists, and that was built in the 1960s. So again, you see, we're not great for energy storage. So hydrogen is the darling of energy storage. It's the thing that everyone will tell you is going to be great. We're going to have the hydrogen economy, it'll save the world. Well, I'm a chemist, and I think that's a load of old rubbish. Let me give you some reasons why I think that's not going to happen. 1 kilogram of hydrogen, in terms of energy content, is the same as 3.5 kilos of petrol. But 3.5 kilos of petrol takes up 4 litres, whereas a kilo of hydrogen takes up 11 cubic metres. So that's something that's roughly about 11 cubic metres. It's a barrage balloon. So you see, if you wanted to store hydrogen to use in your car, basically we'd all be driving around carrying a barrage balloon with us. So if we compressed it to 300 atmospheres, we'd still need a fuel tank 10 times the size of a current fuel tank to get the same distance. And also hydrogen has a nasty habit of attacking storage tanks. So let's say that compressed hydrogen isn't a particularly good way to go. So maybe we could liquefy it instead, which is the other alternative. Okay. Liquefied hydrogen is minus 253. To give you some idea of how cold that is, the coldest temperature ever recorded on Earth, natural temperature, is in Antarctica at minus 89. So you see, we have a long way to go to get down to minus 253. And again, 40% of the energy that's in that hydrogen is used to liquefy it in the first place. So not only have the problem of getting it down to minus 253, we're also going to use almost half of the energy to get it to that state. And then having done that, we're going to use even more energy to keep it liquefied. So I'm of the opinion that hydrogen will never be a good storage source on its own of energy. But there are other ways, fortunately, of getting hydrogen, and you don't have to just have it as neat hydrogen, if you like. And ammonia is a very good way of doing that. So here's our little ammonia molecule up here. It's 3 hydrogens and 1 nitrogen. And actually, the nitrogen, or effectively the nitrogen, is acting as the carrier of these hydrogen atoms. So it can be a hydrogen carrier, it can be an internal combustion engine fuel, and it can be used directly in fuel cells. So you don't have to break it up to get the hydrogen out. You can store it under moderate pressure, about 8 atmospheres, so that's pretty easy to do. And at that pressure, the fuel tanks on a typical car, would be about 3 times the volume and 2 times the weight. So it's certainly not impossible. Ammonia production has been undertaken for 100 years, greater than 100 years. Mr. Harbour and Mr. Bosch did that a long time ago. And unlike methane or methanol or ethanol, which is the type of economies that people are touting as possibles, there's no carbon emissions. There's no carbon in ammonia, so therefore we can use this, we can generate it by green methods, we can use it and we don't generate any carbon dioxide or any greenhouse gases. And to prove that these things work, this is, it's a little bit dark, but this is a internal combustion engine that's been converted to run on ammonia, and you can see it looks exactly the same. They don't have to do a huge amount of alterations to make it run on ammonia. And this is about a year ago, Tata started running a ammonia fuel cell electric car. So that's, again, you can't see it in the image very well. It does actually fill up the entire of the... there's just about space for a driver in there, so you can see there's some miniaturisation required. But that does actually work as using ammonia as a direct fuel for a fuel cell. I'm avoiding the word so. How would we get these things to work? Well, if we wanted to do it completely green, and this is obviously the best way to do it, so we're not going to use any coal or nuclear, if you like, to get the energy required. If we went somewhere hot, so we go to the south of Spain, be quite nice, we can use our alternative energy sources, so there's wind or solar, and we can get our energy. And we need that energy for three things. We need to purify nitrogen from the air by some method. We need to split water down into hydrogen, to get us the hydrogen for the ammonia, and we need heat to actually get the system to go. So here you can see in the tank in the middle, this is a sort of standard ammonia synthesis tank being fitted, and you can see there's a little man here to give you some idea of the scale. Having generated these things, we can use the heat from the sun to heat this process up, and we can generate ammonia. So that process has been around for 100 years, not particularly difficult to do. It's made on megaton scale already, but not by green methods, if you like. So we could actually start having refineries in the south of Spain to make our fuel instead of relying on Arab countries, which are somewhat less stable. So that's one example. Another example is chemical storage. So I'll talk a little bit about the options we've got for how we might store energy in a slightly different way to how you might think about it. So everybody in their pocket has got a mobile phone, I guess. It runs on a battery, and typical batteries have more than one component, chemical component that is. And the problem with that is if you put that battery to one side and leave it for 2 years, when you come to use it, it'll be no good because the chemicals degrade over time. So these flow cells, which is a relatively new invention, probably about a 10-year research cycle as it goes, is looking at using vanadium metal. And vanadium metal is a unique metal in that it has about 4 or 5 fairly stable oxidation states. And what that means is you can use vanadium just in its pure state or as an oxide in a battery, and you don't have any concerns about it degrading. It's always going to be vanadium. It can't be anything else. So this is a schematic of a flow cell and how it might work. You don't have to worry too much about the details, but you see we've got basically a positively charged vanadium one side, negatively charged vanadium on the other, and as the electrons exchange, that drives a circuit, and that's our cell. And here is one that's been set up. So these are, I think, 250 litre tanks. So you can see one that's working. This is being used to smooth power out of a wind turbine. So there are vanadium versions, there's vanadium bromide, and there's these polysulfide bromide. Again, you don't have to worry about it, but you can see there are different versions that allow you to do these flow cells. And the advantage of them is their size is theoretically limitless. So you've seen one there that was about 250 litres. You could make one the size of a football pitch if you wanted to, depending on how much energy is required. There's no charge memory, there's no storage decay. So as long as you keep the two apart, nothing happens to them, and you don't put too much oxygen in there as well. And you can charge them by electricity, or you can recharge them by simply replacing the electrolyte, and I'll come back to that in a moment. As I said, currently it's used for power smoothing in wind turbines and for solar storage. So if you've got your wind turbine that's going and the winds stop, you've still got a power source. You can use these batteries to keep supplying energy. But the replacement of the electrolyte part is the bit I'll come back to, because the key, the interesting part about that is there arises the possibility that instead of going to a petrol station and filling up with petrol, you could go to a petrol station or a fuel station and fill up with vanadium. So actually you can pump your used vanadium solution out, pump in a fresh vanadium solution in 10 minutes and drive away with a 250-mile radius on an electric car. And this looks exciting. It's actually only about this big. It's developed by Fraunhofer, the German research organisation, and the flow cell is just there. So it gives you some idea on an electric car. Well, that's only a remote control car, but still, it gives you some idea of how big these things could be, or how small these things could be. Another type of battery that's being researched along with your lithium-ion batteries in your mobile phones, you'll know that if you've got a smartphone, it lasts about a day, and then you've got to charge it up again. Added to that, lithium is particularly expensive and it's becoming rarer. So the more electric cars that we have, the more demand there is for lithium, so the price goes up, but actually it becomes rarer and rarer. So there are issues with lithium. Sodium, on the other hand, there's a huge volume of sodium about, much more available than lithium, and certainly a lot cheaper. Now, obviously, if the demand on sodium goes up, the price goes up, but it will still be cheaper than lithium. It has a higher theoretical energy storage than lead acid, so this will be a very good replacement, certainly a lot lighter. And it is, again, suitable for large and small energy storage applications. So you could have a sodium-ion battery that was the size of this room, and that would be useful for power stations again. This is really cutting edge. It's only been looked at for about 2 years. As it stands, the issue is the number of cycles that you can put these batteries through, so the discharge-charge cycles, and the best at the moment is about 50, so it has a way to go before it can start competing with lithium. But as I said, this is very, very cutting edge, very new. And if we're looking at thermal storage, so if we had our sodium-ion battery and we want to keep topping that up with energy, we might use something like one of these things. And this is in France. I think this is quite pretty, but other people have said they think it's really ugly. But it's your decision. If you've seen The Man with the Golden Gun, there's a James Bond film, you see this is, again, not so far-fetched, I guess. This is a solar thermal plant, and it's basically collecting all of the heat from the sun and focusing it down into this little building, or this big building really in the middle here. So these are mirrors, and that's the collector. It doesn't need a little cigarette case to make into a gun, by the way. Currently about 1 gigawatt of power in 2012 is generated using this technology. By 2016, there will be enough plants around in Europe to generate about 14 gigawatts. So you can see in a very short period of time, we're going to have a lot of electricity generated this way. But the biggest drawback is it only works in the day. So what we need to do is take this heat, which we're using to generate steam, and store it for night operations. And the way to do that is you've got to store that heat in something that's very thermally stable, because obviously you can't heat up an oil, it will just decompose. So the current way of doing that is to use a salt. A potassium-based salt gets up to about 500 degrees C, and as long as you keep it away from oxygen, it's pretty stable at that point. That heat can be stored for a week as it stands, and the Torresol plant in Spain in 2011 was the first solar power station that achieved 24-hour continuous power generation by pumping this heat away during the day and then bring it back at night. It's a 20 megawatt plant, which isn't huge, but there are larger planned. And if we wanted to do this on a small scale, so we might say you didn't want to store the heat for longer than a week, but at a small scale, if you were doing this in your house, you might want to store it longer than a week. And so actually what they're looking at is thermal storage media that can last up to about a month. So you could, so if you were going through a winter period, you could charge your heat store up in the summer, and then you could have a month's free energy effectively. That's the idea. So here's a list of some other techniques I haven't got time to talk about. I'm not doing too bad. I think some of these will be covered in later talks as well. So we've got supercapacitors and ultracapacitors, which are for generally quite short-term energy storage. Flywheel energy storage, if you've seen anything on NASA, they've spent an obscene amount of money on developing this. And basically it's a vacuum with a big spinning wheel in the middle. When I say it's a big spinning wheel, it spins at 20,000 RPM, and so the materials challenges to make something that can spin at that speed without blowing itself apart is actually pretty impressive. And those things go to space where they're not affected by gravity, and you can just keep extracting energy from them as you need it. So that's useful in space, perhaps not quite so useful on Earth. And we've also got things like ice storage, solar ponds and biofuels, and as I said, that will be talked about a little bit later on. So to recap on what I've talked about, I think energy storage is definitely more important now than energy generation in terms of research that we need to do. And there are lots of technologies with potential, so it'll be a case of things will emerge, some things will fall by the wayside as always. But the key factors are always going to be energy efficiency and energy storage density. So the smaller we can make it, the lighter we can make it, with the highest energy storage capacity, they'll be the things that win out. There will definitely be a difference between the large and small scale applications, but of course cash is king, so at the end of the day whichever seems to be the best and is the cheapest will be the one that people will adopt. And one of the things we're keen to do is to say, what do we think the impact would be on businesses in general? Well, really, the biggest impact would be improved return on investment on renewables. So if you install a solar plant or solar thermal collector, say, or a photovoltaic cell on your building, it only generates your electricity in the day. So in the night, it's completely useless. So for 12 hours, let's say, half the time, it's not doing anything. So if you have a method of storing your excess energy during the day that you can reuse at night, you reduce the return on investment time period for that renewable. In reality, you might not see any change at all, because most of these things will be used at the production scale. So if you're just a user, you'll never see the fact that this solar thermal collector is storing this energy so you get 24-hour electricity. I'd like to say that if they can do that, that makes their process cheaper, and so therefore you get cheaper electricity, but probably not. But possibles are things like, this is a direct methanol fuel cell in a MP3 player. So you might, for example, instead of going down to the shops when your MP3 player's batteries are flat and buying a new Duracell battery, instead you'll carry around a lighter with you, equivalent of a lighter with a fluid in it, and when your batteries are flat, you'll just simply top it up with methanol. This is by Toshiba. They're in the process of commercialising this. The issue is going to be where you can buy methanol from, but they've not talked about that one yet. So Sony and Panasonic also have methanol batteries for laptops, which have I think, the best at the moment was between top-ups is about 16-hour life. So you can see they're significantly better than lithium-ion batteries. The other thing is, as I said, we might start using vanadium oxide as a fuel instead of petrol. So you'll get in your car and you'll drive to your local filling station and you'll just attach a pipe and pump in a vanadium oxide solution instead of petrol. And you'll have electric cars. You can decide whether you like that idea or not. But one thing I'm absolutely certain of is we'll never have a hydrogen economy. And that's the only time that anybody's tried to use hydrogen, not particularly successfully. So, and that's the end of my presentation. So, thank you for listening. Yes?
How plentiful is vanadium?
Vanadium. Well, the nice part with this technology is because it's not ever degrading, so if it doesn't matter if it ends up, most chemicals will end up as an oxide. Well, actually, in this situation, you're using vanadium oxide. So you're only changing it between vanadium 5 positively charged, say, and vanadium 2 positively charged, and it's just an oxidation and reduction. So really, the lifespan of those batteries is huge. So now vanadium is obviously a finite resource. In terms of lithium, yes, it's significantly rarer, but then lithium batteries last for 5 years and then they scrap, and you can't really recycle the lithium particularly easily. Vanadium batteries might last 25 years. So actually, you know, the trade-off there is the lifespan of the battery is significantly longer than with the lithium ion. But you're quite right, yes, that will be an issue. There will be a limited amount of vanadium available.
Can they be recycled after that 25 years?
Yes. So it would end up as, generally with things like with all chemical reactions, it'll be impurities that start to make it degrade. Because you're only starting with a system with one metal in there, the recycling problem's actually not much of a problem at all. You can get the metal back pretty easily.
There was a blaze of publicity about, I can't remember, it was this time last year, some chap announced that he'd figured out how to compress and freeze air as a stored energy source. What's ever happened to that? You mentioned that in there. You
compress that you can. The issue with compressing air is when you put the energy in to start to compress air, you generate a lot of heat. And that heat is actually part of the energy you're putting into the system, if you see what I mean. So if you take a volume of air and you compress it by half the energy you put in there is wasted as heat. So when you take that compressed air and let the pressure out, you can only get 50% efficiency because you've only got 50% of the energy in there in the first place. So what you need to do is have a system whereby you can capture the heat energy that you put in, that the pump generates and that the actual compression part generates. You need to be able to capture that heat energy so that when you then let the pressure out and the air gets cold, you can add that heat energy back. There are ways of doing that. This is, again, pretty cutting-edge stuff in that what they're looking at the moment is potentially pumping it into things like abandoned mines so that the rock acts as the heat store, if you like. In reality, how airtight is an abandoned mine? Don't know. You know, there are issues with that. One of the potentials was hydrogen storage was exactly the same thing. We can pump it into an old mine. Well, that's great till somebody walks past with a cigarette and blows up a huge volume of hydrogen. So actually, I don't know. It's not impossible. There was a thing about a 3-cylinder car, compressed air car that they developed I can't think what the company was, but it was about a couple of years ago that was announced that it existed. Again, the problem is getting the compressed air in it in the first place in an energy efficient way, and its mileage was somewhere in the region of about 30 mile was its distance limit. So around an airport, which is what it was planned for like moving bags about, that's ideal because it's never going to do more than 30 miles. But again, if you looked at what the energy efficiency was for a compressed air car versus a diesel car, the diesel car won out by miles. So that's why it's not really got anywhere yet.
Okay, thank you.
Yeah.
Let's take an island country like Britain as an example. How much storage, given the targets for renewables, will be needed? And who is likely to make this investment?
That's a very good question. Well, in terms of who's going to make the investment, I'd like to think it'll be the energy producers that will find that these things are useful. As I said, so if you've got if you're it might be an end user. So Toyota, for example, at Burniston has installed this huge solar farm that only generates electricity during the day. So at night, when their plant's running, they're now having to run back on the grid power. But their solar plant actually overproduces during the day. So what they really need is some way of storing that overproduction. So for them, it would be a worthwhile investment to have some technology that allows them to store that extra energy and get more return on investment for their solar collectors. If it was a large plant like the Torresol one in Spain or that one I showed you in France, then it would have to be the energy producer that put that in. Yes, whether they would be willing to do that is another matter. In terms of space, it's very difficult to say. And I think it can be devolved, so it doesn't have to be where the generating thing is. If it's part of the grid, you can obviously store energy from the grid in any form. So it doesn't have to be. You don't have to have your vanadium flow cell sat next to your solar collector. It could be thousands of miles away, really. It's a very difficult thing to say. I think to say how much space that would really take up. I don't know. Is the honest answer.
And when do you expect? So just follow-on question. When do you expect energy storage at scale? At scales of, gigawatts, let's say, at the national level, to actually take off? Are we talking a couple of years or a couple of decades?
I would think, what's going to happen very quickly is we're going to run out of space for things like wind turbines. Certainly in the UK we are. They're all going offshore as it stands. There's only so much sea that we've got available before we start running ships into them. So, yeah, we are going to run out of space where we can put renewables. And at that point, we're then going to have to look at how do we store things better. So I think within a decade, we're going to have a lot better methods of storing energy for long periods of time. It's not simply that's a finger in an air number. We can't wait that long, really. The nuclear plants are all being switched off. There'll be a predicted energy shortage by about 2020. So really, we need solutions between now and then.